Hello. This video is on using the power rule to find derivatives. In a previous class, we learned that the derivative of a function is defined to be the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? And so we applied this formula to functions such as x to the fourth. We did that in class. We did it with f of x equals x cubed for homework. And we also did it for f of x equals root x for homework. However, each time you had to apply this definition in order to find the derivative. For x to the fourth, you have to do x plus h to the fourth somewhere along the way. And for square root of x, you have to do square root of x plus h minus square root of x, and you have to do the conjugates. So there were different rules for different times. And so what this lesson is on is to develop a formula, a general formula that would apply in all situations. And so what we're going to start with is f of x equals x to the nth power. So instead of a specific exponent, we're going to put x to the nth power. Okay. Applying the definition of the derivative, we would get the limit as h approaches 0 of x plus h quantity to the nth power minus x to the nth power all over h. Now to keep this video short, I'm going to skip ahead to what this limit equals to after all the expansion and simplification. In class, we went step by step, but on this video, I will just go straight to the formula. It gives you this limit will equal to n times x to the n minus 1 power. Therefore, here is what we have developed in class. If f of x equals x to the n, then the derivative f prime of x is equal to n x to the n minus 1 power. So let's examine what we are actually doing. We are moving the exponent n to the front, and then we are replacing the exponent with 1 less than the original exponent. This is called the power rule. Now, I encourage you to do the in-between steps that got us from this step to this step. It requires the binomial theorem. Okay? All right. So let's do a few quick examples so that you can get used to the power rule. Okay? All right. So example 1. F of x equals x to the 9th power. The derivative will be 9x to the 8th power. All we did was move the 9 to the front, and then we decreased the exponent by 1, and so it became 8. So it's 9x to the 8th power. Okay? Let's look at another example. Let's do x or f of x equals x to the 5/7 power. The derivative is going to be 5/7, so you move that exponent to the front, and then your new exponent will be 1 less than 5/7, which is negative 2/7. Here's another example. Example 3. F of x equals 1 over x. Okay. Well, first of all, we're going to write 1 over x as x to the negative 1 power so that we can apply the power rule easily. The negative 1 exponent comes out to the front, and we decrease the exponent by 1, making the exponent negative 2. So our derivative is negative 1 over x squared. Example 4. F of x equals the square root of x. So first we write f of x as x to the 1/2 power, then we apply the power rule. The 1/2 comes to the front, and then we decrease. Okay, sorry for the interruption. Then we can rewrite this as 1/2 root x. Example 5. F of x equals 7x. Okay. All right, well, we can think of 7x as 7x to the first power. So the derivative is going to be, now the 7 just comes down, and then you move the 1 exponent to the front, and then you decrease the exponent by 1, giving you a 0. 7 times 1 times x to the 0 power is 7. So the derivative, now this makes a lot of sense because if we were to graph y equals 7x, we would have a line that has a slope of 7. And so since it's a line, every single tangent line to this line will have a slope of 7. So that makes sense. Okay? Example 6, f of x equals 5. Okay? So here we have a constant. So we can think of f of x as 5x to the 0 power. Applying the power rule, we're going to just write the 5, and then the 0 comes to the front, and then you have x to the negative 1 power. 5 times 0 times x to the negative 1 power is just 0. So the derivative of 5 is 0. Now this also makes sense because if we were to graph f of x equals 5, we would have a horizontal line at 5, and the slope of any horizontal line is 0. Since the derivative gives us the slope of the tangent line, the derivative is 0. Okay? All right. Now let's find the derivative of something that's a little bit more complex. So let's say I have 5x to the 4th plus 3x cubed minus 2x squared minus 10x plus 7. Okay? All right, so we're going to apply the power rule to every single term. The first term, the 5 just comes down, and then the derivative of x to the 4th is 4x cubed. Here the 3 comes down, and the derivative of x cubed is 3x squared. Here the 2 comes down, and the derivative of x squared is 2x to the first. And then next, the derivative of minus 10x is just minus 10. And then the derivative of plus 7 is just 0. Remember, the derivative of 10x is just 10, and the derivative of 7 is just 0. Kind of like our last two examples. Then we simplify. 20x cubed plus 9x squared minus 4x minus 10. And that will be the derivative. And keep in mind that this formula gives us the slope of the tangent line at any value x. So f prime of 7 will be the slope when x equals 7. F prime of 2 will be the slope when x is 2. Okay? All right. Okay, so now the next example is very interesting. Let's find derivative of sine x. Okay? Now, at first you might think we can't apply the power rule to sine x because sine x is not in the form x to the nth power. But if you recall, sine x has a power series representation. And the power series representation of sine from the previous chapter is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th to the 7th over 7 factorial plus ... So this allows us to apply the power rule to every term here. So the derivative of x is 1. The derivative of x cubed is 3x squared, but there's still this 3 factorial down here, okay? Plus, the derivative of x to the 5th is 5x to the 4th, but there's still this 5 factorial down here. The derivative of x to the 7th is 7x to the 6th, but there is still the 7 factorial down there, okay? Now let's simplify this. We have 1 minus, now 3 over 3 factorial is 2. 5 over 5 factorial is 4 factorial. 7 over 7 factorial is 6 factorial. Plus dot, dot, dot. Now, if I think of 2 factorial, or 2 as 2 factorial, does this look familiar? Well, this is the power series expansion for cosine of x, which means that if f of x is sine x, then f prime of x is cosine x. So the derivative of sine is cosine. That is a very powerful discovery. Lastly, we are going to use the definition of the derivative to evaluate certain familiar limits. For example, if we have evaluate the limit as h approaches 0 of x plus h to the 3rd power minus x to the 3rd all over h, what we will notice here is that this limit really looks like the definition of the derivative, but for the x cubed function. So this right here is the derivative of f of x. So this right here must be the derivative of f of x equals x cubed. And what is the derivative of f of x equals x cubed? It is just simply 3x squared. So by knowing and recognizing that this is the limit definition of the derivative, we don't actually have to do the whole expansion in order to figure out this limit. Now, if we did do x plus h to the 3rd and just multiply it all out and then cancel things and plug in 0 for h, we would get 3x squared. But by recognizing that it's just the definition of the derivative, we don't have to do that. We just know, hey, that's the derivative of f of x equals x cubed, so the limit must be 3x squared. Okay? So, just one more example to reinforce this idea. Let's say that I want this limit, the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. Well, this is the definition of the derivative for f of x equals root x. And on the first slide of this video, we found that the derivative of square root of x is 1 over 2 root x, which means that this limit is just equal to 1 over 2 root x. No need to do the conjugate, no need to multiply things out. Because it fits, because this expression fits in with the definition of the derivative, we just know to take the derivative of root x, and that derivative will be what this limit equals. Okay? So there will be a question on the derivative 2 homework that has several of these for you to do. But it's not that much work because you just have to take the derivative. Okay? All right. That's all, folks.